So, good morning, everyone, and welcome to this lecture. This is lecture number 2, and we are going to start with what is known as Biot Savart law. In the previous class, we had seen some important facts about magnetic field and electric field. We started with a bar magnet. A bar magnet is also known as magnetic dipole. It has a magnetic dipole moment m vector. And we had seen whatever we had seen in electric field, we had seen the counterpart in the magnetic field. We had seen how we can find out magnetic field due to a single pole, north pole or south pole. Single north pole and single south pole do not exist. They always exist in pairs, and therefore magnetic field lines, they do not have a starting point, they do not have an end point, they are always in closed loops. So we remember this. Magnetic field lines are always in closed loops, no starting point, no end point. We had seen the magnetic field due to a monopole, which is same as the electric field due to a point charge. Then we moved on to bar magnet. Axial point, we had seen the value of magnetic field. Equatorial point, we saw the value of magnetic field as well as electric field, and the general point, and that is where we finished the class. Remember, the name of this class is magnetic effects of current. As soon as we understand that the name of the chapter is magnetic effect or magnetic effects of current, that will give us an idea that magnetic field can not only be produced by a bar magnet, but it can be produced by a magnet as well. And that is what was discovered in the year 1820 by a scientist named Oersted. So this is his experiment, which is known as the Oersted's experiment or Oersted's discovery or whatever you call it. Now, what he saw? He saw that whenever you have a current carrying wire, and he was experimenting with a current carrying wire. Uh, there was a current carrying wire, and he brought a magnetic compass or magnetic needle. Do you know what is this magnetic compass or magnetic needle? Magnetic compass or magnetic needle? Magnetic compass or magnetic needle is a short, very small magnet, if I can call it, and it always rests in the north-south direction because it is attracted by the magnetic field of Earth. And this magnetic compass or magnetic needle, apart from staying in the north-south direction, if there is a strong magnet present, which creates its magnetic field, this magnetic needle will start to deflect. Do we understand this, everyone? Magnetic needle. We understand this one?
Yes, sir.
Okay. Magnetic needle can actually detect a magnetic field. When it detects a magnetic field, it will start to deflect. And that is what Hans Christian Ørsted discovered. It's a discovery. Do you know the difference between an invention and a discovery? Yes or no? Invention is when you invent or create something new. Discovery is when you find out something and you just discover it. It was Vasco da Gama discovery of India. Not India was already there. Columbus discovery of America. America always existed. Was Columbus just arrived there? Discovery. So this is Oersted experiments or Oersted discovery. What did he discover or what did he find out? He found out that when a needle, a magnetic needle, is brought near a current carrying wire, it deflects. It deflects, showing the presence of B. You understand the meaning of B? B means magnetic field. So his experiment confirms his discovery, his experiment confirms what? Confirms that a current carrying wire creates magnetic field. And that is why we have this chapter, magnetic effects of current. So a current carrying wire creates magnetic field. What else did he discover? Now, this current carrying wire is creating a magnetic field. Let me call this as B. And because of this magnetic field, the needle is deflecting. What else did he discover? When the current in the wire is increased, what would he see? What he saw? What do you think did he saw when he increased the current in the wire? What will he see? So here you can do it in a lab also. You have a wire and you flow current and you bring a compass near to that wire. When he increase current, what will he see? Or what he saw when he increase current? This is common sense. What will he see? When you increase the current in the wire, what will happen to the magnetic field? Yes? Will it increase? Will it decrease? Or will it remain same? Is everyone there present in the class? When the current in the wire is increased, then what will you see? What will you observe? No one knows it. Okay. When current in the wire is increased, the deflection increases, which implies that the magnetic field B has increased, and vice versa. Vice versa means when the current is decreased, he found out that the deflection decreased and hence the magnetic field, he saw the deflection decreasing. That implies that the magnetic field is decreasing. When the needle is brought close, when he brings it close, then he observed that the deflection in the needle decreased, which implies that the value of magnetic field decreases, and vice versa. Vice versa means, oh sorry, I've written it ulta. When the needle is brought close, deflection increased. So when needle is brought close, deflection increase. That implies that the magnetic field increases, and vice versa. That means when it is taken away from the wire, the deflection decreased. When the direction of current is reversed, the deflection also reverses. Deflection also reverses, which implies that the direction of magnetic field has changed, which implies that the direction of magnetic field reverses. So this was the Orsted experiment, and these were the observations from the Orsted experiment. I'll give you 2 minutes so that you can note them down. That takes us to the next thing. There are a few points, also important points, that will summarize everything. So I will give those points. First, I will give them, then I'll give you time to note them down. Note them down so that you can, these points may come as questions in your exam. First, let me explain them, then I will give you time. Then you can note them down. Point number one is a magnet which is at rest will produce a magnetic field around it. Electric charge at rest produces an electric field around it. Magnet at rest, magnetic field. Electric charge at rest, electric field. We understand this? Electric charge plus Q at rest. What does it create? It creates an electric field. We know this, yes or no?
Yes, sir.
Okay. But when this electric charge starts to move, and we have seen that in the previous chapter, when electric charge starts to move, it constitutes a current. Now we have current. Since we have current, now listen to me very carefully, then I will give you time after this to write, so then you can write. A current carrying wire, which is the point of discussion here, a current carrying wire or a current carrying conductor creates current carrying conductor. It has charges which are moving dig 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 dig. It creates a magnetic field. Ooh. And not electric field. So current carrying conductor wire, it creates magnetic field around it, not electric field. On the other hand, and it is very important for you to understand, on the other hand, a charge moving with a uniform velocity creates electric as well as magnetic field. Remember these points can come in your exam. That means if I have a gentleman charge which is moving with a constant velocity v, remember, constant velocity v, it will create both electric field as well as magnetic field. Do we understand this? Now, now we can have a charge which is accelerating, dig, 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 dig. It has an acceleration, oscillating charge or accelerating charge, which has an acceleration. It produces EM waves, electromagnetic waves. That is the last chapter of this electromagnetism. EM waves, it will create waves, as well as electric field and magnetic field. I'll give you time to write, don't worry. Plus Q charge, which is moving with an acceleration. It creates electric field and magnetic field and EM wave. EM, electromagnetic wave. Now, a current carrying wire creates a magnetic field, but it does not actually create a magnetic pole, but it creates the effect of magnetic poles. How does it create the effect of magnetic pole? Don't worry, we will see that. Right now, what we are more concerned is that you understand all these three things. Have you understood it? Yes or no? No, yes.
Yes, sir.
Now you have time to note them down. If you have any doubts, please feel free to ask me. I'll give you 2 minutes. So now let us move and see the Next part, and the next heading is known as current carrying element. What is this current carrying element? Do not get confused. Just look at the name, because we might be using this term current carrying element a lot of times. Current carrying element. What is this current carrying element? Now, wherever you have a current carrying wire, and this current carrying wire could be in any size, any shape, carries a current I. You take a very small length of the wire. We take a very small length dl of the wire. This is the small length dl of the wire. If I multiply this I with dl, this I into dl is known as the current carrying element. This I into dl is known as the current carrying element. And this current carrying element is a vector actually. It's treated as a vector. Then we must understand what is the direction of this vector. What is the direction of this vector? Any idea? The direction of this vector is same as the direction of current. Do we understand this? The
Yes, sir.
direction of current carrying vector is same as the direction of current. I'll give you 2 minutes to note it down. Well, why we have done this small thing, current carrying element? Because the next thing that is going to come is based on this current carrying element, and that is the main heading of this chapter. One of the two main headings of this chapter, I must confess. The main heading, Biot Savart law. What is this Biot Savart law? Let us suppose I have a current carrying wire I, and I take a small element, and we already know this element is known as small element, small segment. This element is known as what? Huh?
Current carrying element.
This element is known as a current carrying element. And then we have a point P whose distance from this current carrying element is R. And the angle between this current carrying element, because it is a vector, the angle between this current carrying element and this R vector, this R is also a vector, is theta. Now, hence Christian Ørsted found out that a current carrying wire creates magnetic field. Biot Savart went ahead and found out, let us find out how much magnetic field this wire creates. So they divided the wire into small segments. One small segment is known as a current carrying element. It creates a small magnetic field. So let me call that small magnetic field as dB. dB. B for magnetic field, D means small. And then they conducted experiments, and the first thing that they found out that this dB is directly proportional to I. If you want to write it like this dB is directly proportional to dl. So basically you can say this dB is proportional to IDL, and therefore this current carrying element comes. Do we understand this? This
Yes,
dB is again found is inversely proportional to distance square. And one more astonishing thing they found out, that this dB is directly proportional to sine theta, where theta where theta where theta is the angle between what and what?
current and R.
Not current and R, not current and R. dl or I, dl and r. Do we understand what I am saying?
Yes,
I,
sir.
dl and r. Current carrying element and r. We put them together and we have this astonishing formula coming into the picture. dB is I, oops, since proportional design will go out and equal to sign comes in, therefore a constant comes in. And what is that constant? Mu naught, our old friend mu naught. I did not even tell you what is mu naught. Now is the time that I'm going to tell you. Mu naught by 4 pi I dl sine theta divided by r square. That becomes the formula for the magnetic field created by a small current carrying wire or a small current carrying element. Mu naught by 4 pi I dl sine theta by r square. This becomes my original formula. This becomes my formula for what? For magnetic field created by a current carrying segment or current carrying element or small part of a current carrying wire. Here you must remember that this mu naught, which has come many times and no one asked me what is this mu naught. What is this mu naught known as? Huh? No one asked me. We did the entire magnetic field and no one asked me what is mu naught. What is mu naught? It is known as the absolute permeability of free space. Absolute permeability of free space or vacuum. For different mediums, we had different dielectric constants. For different mediums, we have different absolute permeability. We have relative permeability and so on. What is the value of this mu naught by 4 pi? The value of this mu naught is 4 pi into 10 raised to the power minus 7, and the unit can be written in different ways. You can write it as Weber per ampere meter, or you can write it Henry per meter. What is Henry? We will come to know about Henry. Or you can write it as Newton per ampere square, or you can write it as Tesla meter per ampere. Magnetic field due to a small current carrying wire. I'll give you 2 minutes to note it down. If you have any doubts, please feel free to ask me. Then we move ahead. Now, remember, we have already seen that what magnetic field is a vector quantity. Now, this equation that we have made or that we have seen, what does this equation give me? Now I've written the equation I've written the equation dB is equal to mu naught I dl sine theta divided by 4 pi mu naught divided by 4 pi into r square. Now this is the equation that we have written. Now we must understand that this equation that we have written, magnetic field is a vector quantity. What does this equation give us? Does it give us the magnitude of magnetic field, or does it give you both magnitude or direction, or does it give you the direction of magnetic field? What does this give you? Magnitude or direction or both? What does it give you? It only gives us the magnitude of magnetic field, this will only give me the magnitude of magnetic field, and therefore I call this equation as the scalar equation of magnetic field, and therefore I have not written the arrow, the vector wala arrow on this magnetic field, because this is a scalar equation of magnetic field. It only gives me the magnitude of magnetic field. Now if there is a scalar equation of magnetic field, then the next question that comes to our mind is there a vector equation of magnetic field? Is there a vector equation of magnetic field? And the answer is yes, definitely yes. There is a vector equation of magnetic field as well, and in vector it is written like this: dB vector will be equal to mu naught into I dl vector cross r vector. So there is a cross product here, divided by 4 pi divided by r cube.
Sir, your screen is paused.
Oh, I forgot. This equation is written in the vector form. This equation is written in the vector form, and this equation is written in the vector form, and this gives us both the magnitude and direction of magnetic field, and therefore this equation I will call it as vector equation, because it gives me both the magnitude as well as the direction. Both the magnitude as well as the direction. This equation can be written in one more form. I can write this as dB vector is equal to mu naught by 4 pi I dl cross unit vector r divided by r square, because unit vector r is r vector divided by r. So I can also write it in this way. Whether you write it in the first way or you write it in the second way, the meaning remains same. This is the vector equation which gives us both the magnitude as well as the direction of magnetic field. But we are not going to use this equation unless it's a emergency. We will not use this equation. We'll only use the scalar equation. Now, if you are going to use the scalar equation, you will need some way to find out the direction of magnetic field. How will I get the direction of magnetic field? So I must find out some way to get the direction of magnetic field. And how do I get the direction of magnetic field? The direction of magnetic field is given by RHT rule. Have you heard this term RHT? Right hand thumb rule. The direction is given by right hand thumb rule. And how do you apply this right hand thumb rule? You have to find out the direction of the cross product of dl with r. You have to find out the direction of cross product of dl with r, and this direction of cross product of dl with r is found by the right hand thumb rule. Anyone has any idea what is this right hand thumb rule or right hand palm rule? Right hand thumb rule or right hand palm rule? Anyone has any idea? Have you noted this down, everyone? Have you noted down this, everyone?
Yes, sir.
Anyone knows what is this right hand thumb rule or right hand palm rule?
The direction.
It will give you the direction of cross product. It will give you the direction of cross product. Now, what is this right hand thumb rule? We will discuss it in details in the next class, but we will just, I'll just give you a right hand thumb or right hand palm rule, whatever you call it. Now, this right hand thumb rule or right hand palms rule gives you the direction of cross product of two vectors. Suppose I have to find out the direction of cross product of A cross B. I have to find out the direction of A cross B. So what do I do? You have your right hand. Everyone has just one right hand. You point your thumb in the direction of first vector. The first vector is your A vector. So you put your thumb, right hand thumb in the direction of first vector. You spread your palms in the direction of second vector. In the direction of first vector, you have your thumb. In the direction of second vector, you have your palm. If A cross B is C, then the direction of C would be given by the direction in which your fingers turn. First vector, if the second vector is here, second vector, first vector, second vector, and this is the cross product. Do we understand what I'm saying? First vector, second vector, cross product. First vector, second vector, cross product. If first vector is here, first vector, if second vector is here, second vector, first vector, second vector, cross product. Do we understand this? Because these three are three perpendicular directions. Do we see?
Yes, sir.
Right hand thumb rule, thumb, palm, cross. The direction of your fingers will give you the direction of your magnetic field. Now, how we are going to apply it? How we are going to apply it for the magnetic field? Well, in case of your magnetic field, your first vector is your dl vector. In case of magnetic field, your first vector is your dl vector. So your second vector is your r vector, and dl cross r will give you the direction of magnetic field. So your thumb will go in the direction of dl vector. Your palm will go in the direction of r vector. Then the direction in which your fingers turn will give you the direction of magnetic field. Do we understand this? What I am telling you? This is the most important part of this chapter, this right hand thumb rule. If you can understand this, everything looks good. We understand this. Now, this is an example which I am giving, and it is coming on your board now. Suppose you have a current carrying wire carrying current like this, which is shown on your board, and you have to find magnetic field. This is your current carrying wire, and you have to find magnetic field at this point here. Did you get the scenario of the diagram that is given in the figure? Yes or no? This is your current carrying wire, and this is your point. Do we see this?
Yes, sir.
How do I find the direction of magnetic field at this point? I hold this current carrying wire in my right hand, and my thumb will point in the direction of current. This is the direction of current. My thumb will go in the direction of current. Do you see it in the diagram? Do you see it in the diagram? Thumb, direction of current, which is the direction of DL, and my palm will go towards this point. Point is here. Thumb in the direction of current. Palm is pointing towards the point, and you can see the fingers are coming towards me, and that is the direction of magnetic field. DL, this is the direction of DL, which is the direction of current. Do we see this? Yes or no?
Sir, can you share the screen?
Oh, have you understood what I was telling you?
Yes, sir.
Okay, now you can look at the screen. I thought you had drawn the diagram. You have not drawn the diagram. Okay, now here is the diagram. DL. DL is in the upward direction. Do you see DL in the upward direction? And you
Yes.
can see your thumb coming in that upward direction. This is your thumb, T. R vector, in the direction of R vector, your P goes. You can see this is the direction of R vector where your P goes. You understand this? And then you turn your fingers. This is the direction outwards. Your finger will turn, coming out of the board, coming out of the board, coming out of the board, coming out of the board. Do we understand this? This is this. This is this. And this is this. Do we understand this?
Yes, sir.
That is how you find the direction of magnetic field from the right hand thumb rule using the direction of current, where the point is, and the magnetic field DL, R, DL cross R, DL, R cross, DL, R cross, DL, R cross, DL, R cross. Do we understand this? First vector, second vector, cross product. We will use this in the next class to find out the direction of magnetic field in various cases. Don't worry. Try to practice this. First vector, second vector, cross product. First vector, second vector, cross product. First vector, second vector, cross product. Do we understand this?
Yes, sir.
I'll see you in the next class. We'll go ahead with this. Take care. God bless all of you. Bye bye.